Precalculus 3 video lecture number 26 on change of variables in multiple integrals. Now, one of the many useful methods for evaluating functions of a single variable was a change of variables, sometimes called AU substitution. So let's revisit how we applied U substitution to evaluating definite integrals. So say you have the integral from 0 to 1 of x squared plus 2x cubed raised to the third power dx. Well, instead of evaluating this integral directly and expanding the integrand, which would be messy and tedious, we notice we can make a change of variables by letting u equal 1 plus 2x cubed. And then that would mean du is equal to 6x squared dx. I notice I have an x squared and a dx, so that means 1/6 du is equal to x squared dx. And then before I'm ready to make my complete change of variables, I have to figure out what my new limits of integration are going to be. And so substituting in the lower limit of 0, u of 0 would equal 1 plus 2 times 0 cubed, which is 1. And then similarly, u of 1 would be 3. So now I'm ready to rewrite my integral. It's going to be 1/6 times the integral from 1 to 3 of u cubed du. And then it's pretty painless to figure out that that's going to come out to 10/3. All right, well, there's 3 things in particular I want you to notice about this process. One is that when we made the change of variables, the integrand was simplified, meaning the stuff we were integrating became a lot nicer to work with. Instead of having this whole mess, all we had to do was anti-differentiate u cubed. Way better. Second thing I want you to notice is that the differential was changed. So we went from dx to what it was equal to in terms of du. And lastly, our limits of integration changed. Okay. So now we want to consider how a change of variables can be useful in multiple integrals. And we're going to emphasize its use in double integrals, but the methods that we're going to consider extend naturally to 3 dimensions as well. So first, let's talk about how we integrate when we're dealing with double integrals. Well, we integrate over a region, typically in the xy plane, and through an appropriate substitution, we're going to transform this to a region in the uv plane. Okay, so first let's talk about transformations. We're going to require a very specific transformation in order for this process to work. That's why it says through an appropriate substitution. So what's appropriate? Well, here we go. We're going to define our transformation as capital T of uv, and it's going to equal some xy, meaning you plug in some point uv in the uv plane, and the transformation is going to spit out some point in the xy plane. This might seem backwards, but just hang on a second, okay? Now, first thing that we're going to require is that T is 1 to 1. What does that mean if it's 1 to 1? Well, that means if you have 2 different points, so no 2 different points or different inputs, so that would be u1, v1. How do I say it's different from something? It's not equal to u2, v2. So if you have 2 different points, they should not have the same image. They wouldn't map to the same xy. If you haven't heard the word image before, you could think of it also as output or range. All right, now do you remember why we cared whether or not things were 1 to 1? Well, if they are, then that means they're invertible. So what does this tell us? T inverse exists. Ooh, now we're excited. Okay, so we need to define things a little bit. Let S be a region in the UV plane. All right. Then if I apply my transformation to the entire region S in the UV plane, I get R. Where's R live? That region R? R is a region in the XY plane. But you might say that's not the way I want to go, right? So T of UV maps to some XY, but we want to go the other way. So t inverse of xy will map us to some uv. And the fact that it's 1-to-1 means that I know this is going to be well defined. Also, since t inverse exists, that means I can solve x and y in terms of u and v. And I do require something else. So that means I can write x as a function of u and v, and I can write y as a function of u and v, and we require that they both have continuous first partials. All right, good stuff. So let's see exactly how this would work, just generally speaking, and then we'll look at applying it to integration. Okay, one step at a time. So here's our first example. Given S is the square bounded by the lines u equals 0, u equals 1, v equals 0, and v equals 1, find R, which is the image of S under the following transformation. X is equal to v, and y is equal to u times 1 plus v squared, and then sketch both regions. So I'm going to start off by sketching my region S in the uv plane, and it's bounded by 4 different lines. And notice I'm just going to be in the first quadrant. Okay, I'll put u here horizontally and v vertically. So u equals 0, that would be the u-axis. U equals 1, that would be up here. No, excuse me, that's v equals 1. Here's u equals 1. And then v equals 0, that's the v-axis, and then here's v equals 1. All right, so where's the region S? It's right here. How many curves make up its boundary? I see 4. So I'll call this S sub 1, S sub 2, S sub 3, and S sub 4. All right, and you want to make sure you traverse the region exactly once. So I'll put a counterclockwise orientation. You don't want to double count anything or leave the region open for some reason. Okay, so let's see how the transformation is going to take place. You do it by boundary piece at a time, meaning I'm going to take S1 and apply the transformation that was given here, that x is equal to v and y is equal to u times 1 plus v squared. So what's the equation for S1? Well, it's u equals 1. So if I transform that to R1, to the boundary in the xy plane bounding my region R, let's see. Well, they tell me x is equal to v. That's not really relevant. But I could use the other equation, y equals u, which is 1, times 1 plus v squared. But I know v is equal to x, so 1 plus x squared. So this just gives me 1 plus x squared. All right, interesting. What about S2? So S2's equation is v equals 0. Well, what would R2 be? Let's see what's relevant. Well, if v is equal to 0, I know that means x is equal to 0. All right, very nice. 2 more to go. So S3, that equation is given by u is equal to 0. Well, if u is equal to 0, that means y is equal to 0. So R3 would be y equals 0. And S4, that has the equation v equals 1. And so R4, if v is equal to 1 and x equals v, that would just be given by x equals 1. So now I'm going to put together R1, R2, R3, R4 in the xy plane and see what they bound. And that's going to be my region R. So I've got this parabola opening upward, shifted up 1 unit, and it looks like everything else is positive. So I'm going to stay primarily in the first quadrant. There we go. So here's my x-axis, here's my y-axis. I'll say this is 1, this is 2, and this is 1 as well. All right, so let's draw our parabola. Let's go in order. So R1, parabola opening upward. That looks beautiful. So this is R1. R2 is x equals 0. Okay, so that means y-axis is part of my boundary. That's R2. R3 is y equals 0. Ooh, no, no, no. Come back. So x-axis is part of my boundary. So this is R3. R4 is x equals 1. Okay, so that's R4. Can you see what region they enclose? I hope so. It's right here. So this is the region R. And then here's the region S. Notice S is the simpler region, right? Wouldn't you much rather integrate over a cute little square than this shape here in the XY plane? All right, let's look at one more. Given that S is the disk, u squared plus v squared is less than or equal to 1, find R under the transformation x is equal to au and y is equal to bv. So first thing, I'm going to draw my region S. It's basically the unit circle, right? I'm just going to plot it in the UV plane now, and all the points on and inside that unit circle. So here we go. Looks good. Let me indicate that this is 1, 1, 1, negative 1, negative 1. And so S is everything on and inside there. All right. What is the equation of the boundary? Remember last example, we broke up the boundary into 4 segments. I can just easily express the equation of the boundary as u squared plus v squared equals 1, right? All of the points on that circle. And remember, the transformation I need to apply is x is equal to a times u and y is equal to b times b. So let's go ahead and do that. That means u is equal to x divided by a, and v is equal to y divided by b. All right, so now I have x over a squared plus y over b squared is equal to 1 if I apply the transformation to the boundary. And what does that give us? Well, now we have an ellipse in the xy plane. So let's go ahead and plot that. It's centered at the origin, but instead of a nice relaxing circle, we've got this ellipse. So in the x direction, a, negative a is the distance, y direction, b, negative b. And here's my ellipse. And this is the region R. Okay, good. I think we got the hang of it. Now, typically, we're going to transform a region in the xy plane, one that's awkward to work with, into one in the UV plane. So we want to consider now, how is dA going to be impacted by the change of variables? So remember, our transformation T mapped from the UV plane to the xy plane. So we're going to start there. The UV plane is the nice plane. That's the plane that we want to integrate in. Okay, well, what would be, if you had it your way, and you were evaluating a double integral, what kind of shape or region would you want to integrate over? A rectangle, you say. I agree, right? Okay, so here's my beautiful little region, and say I chopped it up into a lot of smaller bits, and I'm just going to look at a small increment delta s. Okay, so we're in the UV plane. That means the distance along the base is delta u, the height is delta v. And if I wanted to express what these points are, we'll call this left bottom endpoint u naught v naught. And then over here on the bottom right, we have u naught plus delta u v naught. All right, and then our transformation T, remember, takes this region, and then now it's going to map it into the xy plane. So here's the y-axis. Here's the x-axis, and this one's not so nice, okay? The region R is not so friendly, and I'll chop it up into a little bit that's still not so friendly. So we've got this region, I don't know, I'm just drawing some sort of shape that's not as nice as a rectangle, and here are the vertices, okay? And this is x naught, y naught, etc. This is my little delta R. All right, so now I'm going to define R of uv to equal xy, the vector. So basically, R is the position vector of the image of the point uv. So the image or the output of the point uv into the xy plane. All right, so let's think about here two vectors that are going to help me evaluate what delta R is equal to. Remember, I want to see how dA is impacted. Well, I know what dA is in the UV plane. It's pretty easy. It's just a rectangle. But what happens here in the XY plane? So in order to begin my process, I'm going to create two vectors that are going to help me approximate delta R. I'm going to call this vector A, and then this tangent vector here, B. Okay, what are A and B? Let's think about it. So vector A, notice it starts at x naught, y naught, and it stops wherever T maps U plus delta U V naught into the XY plane. So it would be at R of U naught plus delta U V naught, right? So I'm plugging in this point into my transformation. It's sending me over here minus R of U naught V naught. So I did terminal point minus initial point. Remember, R of U naught V naught is x naught y naught, right? Okay, so that's vector A. What about vector B? Similarly, that would be R of U naught. Now that one's changing in the y direction, so it would come from a change in V. So U naught V naught plus delta V minus R of U naught V naught. Okay. So what do I want to do? Well, I want to see what happens as I let delta U and delta V go to 0. So the limit as delta U approaches 0 of R of U naught plus delta U V naught minus R of U naught V naught, so that's my vector A, divided by delta U. Does this look familiar? This is our partial derivative with respect to U. And what does this tell me? Well, if you'll remember from when we studied differentials, if delta U is small, this means that R of U naught plus delta U V naught minus R of U naught V naught is approximately equal to the partial with respect to U times delta U. So my vector A is approximately equal to the partial of R with respect to U times delta U. And similarly, vector B would be approximately equal to partial of R with respect to V times delta V. Well, why do I care about these vectors A and B? Well, remember, if I take their cross product and then take the magnitude of that cross product, that gives me the area of the parallelogram that's formed by those two vectors. And while that's not going to be perfectly giving me the area of delta R, it's going to give a good approximation. So this tells me that the small piece of area delta A, which is delta R here, is approximately people, equal to the magnitude of A cross B. Okay, well, let's do it. What's this cross product going to be? Time for a color change. So magnitude of A cross B is equal to, well, remember A was approximately partial with respect to U, delta U, and then we're going to cross that with partial with respect to V, delta V. Well, the only vectors involved are there, so let's just focus on those. The other two are just going to be scalars, delta U and delta V. So I have the cross product of partial with respect to U, partial with respect to V, and then we have delta U times delta V. All right, so now let's go ahead and find what the magnitude of partial with respect to U crossed with partial with respect to V is. Remember how to do that? I'll set up the whole 3 by 3 determinant. So partial with respect to U crossed with partial with respect to V. We have here an I hat, a j hat, a k hat. Partial with respect to U, remember, who was our friend R? R took UV, it mapped it to a position vector in the xy plane. So the partial with respect to U would be del x del U, del y del U, and then there's no third component, so that gets a 0, okay? And then partial with respect to V would just be del x del V and del y del V. And remember, since we required the transformation to be 1 to 1, then I can solve for x and y in terms of U and V. And this is also why we required continuous first partials, so we could take all of these partial derivatives right now. Good. Now let's do this cross product. First component, 0. Second component, 0 again. Third component, del x del U times del U del V minus del x del V times del y del U. Okay, now we take the magnitude and what do we get? Let's see. Well, the sum of the square of the first two components is just going to be 0. So all I'm going to be left with is the absolute value of the last component, right? Because I'm going to square it and then take the square root again. So I have del x del U, del y del V minus del x del V, del y del U. Absolute value. Usually, this is written as the absolute value of the following determinant. Yes, del x del U, del x del V, that makes up the first row of this 2 by 2 matrix here, whose determinant we're taking, and then del y del U, del y del V, and we take the absolute value of this bad boy, okay? It has a special name. It is called the Jacobian, named after a mathematician whose last name was Jacobi. I highly recommend you look him up. Charismatic, cool dude. Okay, what's our notation? How do we represent the Jacobian? Do we write out the word every time? No, you just write del xy over del uv, and it means do this, okay? So dA is given by, remember you need the absolute value of this determinant, so we write the absolute value outside, del xy del uv times du dv. Where did the du dv come from? Right up above. Hold on. Here we go. So we got the magnitude of this cross product. That's the absolute value of the Jacobian. And then in the limit, delta u and delta v become du dv. Cool. So here's our formal definition. Let's put it all together. The Jacobian of the transformation t given by x equals g of uv And y equals h of uv is as follows. So you have del xy over del uv is equal to, then you take the determinant, that's why we've got those straight lines, del x del u, del x del v, del y del u, del y del v. This is the Jacobian. However, when you find dA, you have to remember to take the absolute value. So you use the absolute value of the Jacobian when you're integrating and you're finding dA. Okay? So here's our definition for change of variables in a double integral. Suppose that t is a C1 transformation. C1 means, you remember, continuous first partials. We like to abbreviate everything in math, right? Why not? Whose Jacobian is non-zero. Okay, so this determinant can't be zero, and it maps a region S in the UV plane onto a region R in the XY plane. Suppose that F is continuous on R, and that R and S are type 1 or type 2 plane regions. Suppose also that T is 1-to-1, except perhaps on the boundary of S. Then we have the following. So our double integral over the region R of f of x, y, dA can be transformed into the double integral over the region S in the UV plane. So you're going to replace x and y so that they're in terms of u and v. And then here is the absolute value of the Jacobian. Don't forget that. Crucial, crucial. And then du dv. All right. Fun stuff. So here's a little cool application that you may not have noticed until right now. Verify that the conversion from rectangular to polar coordinates in a double integral is just a special case of a change of variables. So remember, in video lecture covering double integrals in polar coordinates, we developed our reasoning to figure out what dA would be in polar, and we know it's r d theta. But now we're going to see that it's just a special case of a change of variables. So how do you change from xy plane to polar? Well, we just use the fact that x equals r cosine theta and y is equal to r sine theta. So let me figure out what the Jacobian would be for this transformation. So I need del xy over del r theta, and I'll write it all out. I think it's a good idea. So you have del x, del r, del x, del theta over del y, del r, del y, del theta. And then let's go ahead and figure out what that's going to be. So partial derivative of x with respect to r, that's going to be cosine theta. And then partial with respect to theta is going to be negative r sine theta. Now if I take the partial derivative of y with respect to r, it's just sine theta. And then partial derivative of y with respect to theta is r cosine theta. All right, and then let's go ahead and take this determinant. So I'm going to have r cosine squared theta plus r sine squared theta, which is just going to be r. So this means that dA is equal to the absolute value of r dr d theta, which is what we knew from before. And I recommend in your spare time, remember we figured out what dA was in spherical coordinates, right? Well, why don't you prove it to yourself? Find the Jacobian for transforming from the XYZ plane to rho theta phi. Do it. You'll love it. All right. Are you ready to get into some actual integrals where we apply this? Here we go. So first example. R is the triangular region bounded by 2x minus y equals 2, 2x plus 3y equals 10, and y equals 0. Find its image S under the following transformation: u equals 2x plus 3y and v equals 2x minus y, and then sketch both regions and find the Jacobian. Okay, so we're not actually integrating it. We're just transforming it, finding the Jacobian. Here we go. Let's sketch the region R. And we've got 3 lines that are bounding the region. Okay, So I'm going to plot, it looks like all the action's going on primarily in the first quadrant. Okay. X-axis, y-axis. So R1 is going to be the line 2x minus y equals 2. So slope on this line is 2. Y-intercept is -2. All right. What about the second line? R2. That's 2x plus 3y equals 10. Okay, easier to plot it using intercepts, which are 5, 0, and 0, 10/3. And then R3 is y equals 0. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's just go to 5 as well. Why not? Sounds good to me. Okay, so R1 has y-intercept -2. Excuse me. There we go. And then slope is equal to 2. All right. So y-intercept -2, up 2 over 1, up 2 over 1. Here's R1. Oh, good. And then let's see, R2 has intercepts 5, 0, and then 0, 10/3. So somewhere around here. Looks good. This is R2. And then R3, y equals 0. We got it. So we've got the triangular region. Here is R. Very nice. Okay, let's transform this guy into the UV plane we go. So S1, so the equation R1 is 2x minus y equals 2. Well, notice 2x minus y is equal to v, so that would be v equals 2. S2, so I'm going to take 2x plus 3y, which is equal to 10, but 2x plus 3y is equal to u, so that would be u equals 10. Now, what about S3? This one's a little trickier. So y is equal to 0. So if I substitute in 0 for y into both equations, then I get u is equal to 2x, and I also get that v is equal to 2x. Well, I need, an equation exclusively in terms of u's and v's, but this would mean that u is equal to v. Can we sketch this? I certainly hope so. So here's my v-axis. Here's the s-axis, u-axis, what am I saying? Okay, and then we'll have to go up to u equals 10, which means I'm going to have to go up to v equals 10. 2, 4, 6, 8, 10, right here. 2, 4, 6, 8, 10, boom. And then I also have u equals v in the mix. All right, let's draw that one first so it looks the best. Something like this. Okay, so that's going to be S3. That's u equals v. S1 is v equals 2. So this would be S1. And then S2 is u equals 10. Oh, I wanted it to be perfect. So we'll just scoot that over and say that's 10. This one needs to move a little bit now. Okay. Good. So can we identify our region S? It's right here. Lovely. Here's S. And oh, this is S2. Don't let me forget. Okay, looks good. Now I need to find the Jacobian. All right, well, remember the Jacobian is del xy over del uv. So I have to take partial derivatives of x and y with respect to u and v. So I have to solve x and y to be in terms of u and v, and at the moment I have u and v in terms of x and y. So we got to fix that. So here I know that u is equal to 2x plus 3y, and v is equal to 2x minus y. Best bet is usually subtract them and add them. So notice what I'm going to do here. So u minus v, that's going to cancel out x, right? U minus v is going to equal 4y. Okay, that means y is equal to 1/4 times u minus v. Good, half the battle's over. Now I want to solve x in terms of u and v. So how would I get rid of y? Well, I could take u plus 3v. Okay, u plus 3 times v, y is going to cancel out, and I'm going to be left with 8x. That means x is equal to 1/8 times u plus 3v. All right, so we're going to use these now so we can get our Jacobian. All right, so partial of x with respect to u, that's going to be 1/8. And then partial of x with respect to v is going to be 3/8. And then repeat for y, you're going to get 1/4 and negative 1/4. All right. Now from here, take the determinant. I have negative 1/32 minus 3/32. So that's negative 4/32, which is negative 1/8. That's the Jacobian. That's all the problem asked us for. But I want you to be careful. If you were to actually set up your double integral over s, for f of, remember you'd have to change f to be in terms of u and v, you need the absolute value of the Jacobian and then du dv. So watch out for that, okay? These are attentive little eyes. Now I wanted to show you one little sneaky thing that not all books mention, okay? If you were to find del uv del xy, okay, what would we get? Meaning you didn't solve for x and y in terms of u and v. So you just took partial derivatives right off the bat, but you inverted things, then you would have 2, 3 for your top row, 2, negative 1. So this would equal negative 2 minus 6, which is negative 8. Now what do you notice? It's the reciprocal of the Jacobian. So if you don't have to actually evaluate the integral, you could use this as a shortcut. But when you have to evaluate the integral, you need to find x and y in terms of u and v anyways. Okay, so you can't skip this step all the time. But it may be useful in a pinch. Sometimes you have a really ugly little problem coming at you. Good. Now, don't you want to pick the transformation yourself? Aren't you feeling a little gypped that it was done for you? I would be. So here we go. Let R be the quadrilateral with vertices 0, 1, 1, 3, 3, 1, and 2, negative 1. We're going to evaluate the double integral over R of 2xy dA. Include sketches of both regions R and S. So they're not telling us to apply transformation, but that's what we're going to do. So let's draw this quadrilateral and hop to it. So here's the y-axis. Here is the x-axis. Good stuff. And I'll go up to 4. Why not? 1, 2, 3, 4. 1, 2, 3, 4. Okay. So we've got 0, 1. Boom. 1, 3. Very good. 3, 1. And 2, negative 1. All right. So here's the quadrilateral. Yeah, I mean, who wants to do a double integral over this quadrilateral? You'd have to break it up, right? This piece, super annoying. Don't recommend. Okay, so here's the region R. So where to begin, right? How do you even know like what transformation to pick? Well, it's based off of the equations of the boundaries. That's my best advice to you. So here's R. I'm going to label it. The boundary has 4 pieces, right? Here's R1, R2. I'm just numbering them however I feel like. R3 and R4. Okay, so I'm going to find equations to represent each of those line segments. And then usually the transformation, the best transformation will reveal itself. What do I mean? Just wait and see. Okay, so R1 connects the points 0, 1 with 1, 3. Okay, so that's a line segment. The slope is 2, y-intercept is 1. So that's y equals 2x plus 1. R2 connects the points 0, 1 and 2, negative 1. Okay, so y-intercept is 1, slope is negative 1, so that would be y equals negative x plus 1. What about R3? That connects the points 2, negative 1 and 3, 1. So slope is 2. The y-intercept is going to be -5. So that would be y equals 2x minus 5. And then R4 connects the points 3, 1 and 1, 3. And that has slope -1, intercepts at 4, so y equals -x plus 4. And you might be like, I really don't see a transformation appearing. A good hint is put these equations in standard form for linear equations. Remember what that is, right? You put x first, then y, keep your x positive on one side of the equation. So we'll have 2x minus y equals -1. This is going to become x plus y equals 1. R3 is going to be 2x minus y equals 5. And then R4 is going to become x plus y equals 4. Ooh, do you see a nice transformation we can apply? Look, do you see a common theme? I see 2x plus y, 2x minus y, 2x minus y. And then again, I see x plus y, x plus y. So I think an appropriate change of variables would be to let u equal 2x minus y, and then v could be x plus y. Okay, so then let's rewrite the region, the boundaries in the UV plane. So S1 would become u equals -1. S2 would become v equals 1. S3 would be u equals 5. And S4 would be v equals 4. Now let's see. These are all constants, right? So we're going to get this cute little rectangle in the UV plane. Let's draw it out. Here's u axis, v axis. How far do we got to go, people? -1, 1, 2, 3, 4, 5. And then 1, 2, 3, 4. Love it. Okay, S1 is where u equals -1. There's S1. S2 is where v equals 1. I'll just do them all the same color. Here's v equals 1. So that's S2. S3 is where u equals 5. Here's S3. And then S4 is where v equals 4. Beautiful. So here's our region S. I'm going to shade it in. Okay, and then obviously it would be super nice to set up an integral over this region. You only need one, and all your limits would be constant too. That's relaxing. Okay, well, I need the Jacobian. And then the other thing is I'm going to have to rewrite my integrand to be in terms of u and v. So I do need to solve and find x and y in terms of u and v, since I'm actually going to go through and evaluate the whole integral. Remember, you can just start off by trying to eliminate x or y, right? So if I add them together, I'm going to eliminate y right off the bat. That's cool. So u plus v, that's going to give me 3x, which means x equals 1/3 times u plus v. And then I want to take u minus 2v. That would give me -3y. So that means y equals -1/3 times u minus 2v. All right, let's go ahead and get our Jacobian now. So del xy over del uv. So partial derivative of x with respect to u, that's going to be 1/3. Same for v. And then partial of y with respect to u is going to be -1/3. For v, it's a positive 2/3. Then we take the determinant. So this is going to be 2/9 plus 1/9, which is 1/3. Okay, so that's our Jacobian. I'm going to throw that in my dA. So putting it all together, our double integral over r of 2xy dA becomes the following. We're going to have the double integral over s of 2. Now what was x? X was 1/3 times u plus v. Did you forget already? X is offended. It's right here. Okay, that's x. What was y? Y was -1/3 times u minus 2v. And then I'm just going to leave dA for now. Okay? Now, it doesn't matter if I do du dv or dv du because all of the limits are constant, right? And from here, just make a decision, okay? So look at your region. I'll just do du dv, so I'll have limits for v outside last, so v should go from 1 to 4. U is going to go from -1 to 5. And then I'm still going to have 2 times 1/3 times u plus v times -1/3 times u minus 2v. And then remember, dA is 1/3. There's the absolute value of my Jacobian, du dv. Here is dA. All right, what to do next? Take all those nasty constants outside, right? 2/3, a -1/3, and another 1/3. That gives me a -2/27 sitting outside. Then you're going to have integral from 1 to 4, -1 to 5, u plus v times u minus 2v, du dv. And then what would you do from here? You guys, you have to multiply it out. So you would multiply this out so that you get u squared. It would be minus uv minus 2v squared. And then you just go from there, okay? So have at it. That's really all I need to show you. And that wraps up that first example. Okay, here we go. Let R be the region bounded by y equals x, y equals x minus 1, x plus 2y equals 0, and x plus 2y equals 2. Evaluate the double integral over R of x plus 2y over cosine of x minus y dA, and then include sketches of both regions R and S. Alrighty, here we go. So R1 is given by y equals x. I'm going to rewrite it, standard form, x minus y equals 0. R2 is given by y equals x minus 1. I'll rewrite that as x minus y equals positive 1. R3 and R4 are already in standard form, so R3 is x plus 2y equals 0, and then R4 is x plus 2y equals 2. Do you already have a feeling for what the transformation would be? I mean, look at what you're integrating as well as what you have here for R. I see x plus 2y as a recurring theme and x minus y as well. So it seems like it should be a good choice to let u be x minus y and v be x plus 2y. Obviously you can interchange them, nothing dramatic would happen. Okay, so let's sketch the region R. So we've got these 4 lines to plot, and we're going to do so carefully, of course we will. So here's the y-axis. How high up do we need to go? I think 2 should do the job. And we'll go down to -1. Here's x-axis. So 1, 2. There's -1. And then x-axis 1, 2. All right, let's plot everything. So first line is y equals x. That's R1. Okay. There's R1. Very good. Y equals x minus 1. So same slope, just shift the line down 1 unit. So now all the points are going to just translate 1 unit downward. There's R2. They should be parallel. R3, well, let's see here. The slope is -1/2, and it goes through the origin. So -1/2 is the slope. This is R3. All right. And then R4 is parallel. It's just been shifted 1 unit up as well, right? Same slope. Okay. There's R4. Very good. So what does this region look like? It's a diamond. Ooh. Here's R. As you can see, if you were to try to just evaluate the double integral as is, you'd have to break it up. 1, 2, 3, yuck. Here's r. So let's change it into something nicer in the UV plane. We already picked our transformation. Looks good. Let's figure out what each of the boundary equations are going to be for the region S in the UV plane. So S1 would translate to u equals 0. S2 would be u equals 1. S3 would be v equals 0. And S4, v equals 2. So we're going to get a nice little rectangle. What more could we ask for? Okay, v-axis, u-axis. U is going to go from 0 to 1. V is going to go from 1 to 2. So u equals 0. No, u equals 0 is right here. That's S1. U equals 1. That's right here. S2. Here's v equals 0. S3. And then v equals 2. S4. Here's our region S. I'll shade it in. And it looks good. Yeah, definitely love to integrate over this guy. All right, now we have to figure out what x and y are going to be in terms of u and v. So remember here, let me copy this. Copy, paste it down here. So if I subtract the two equations, u minus v, x will cancel out and I have negative 3y. That means y equals negative 1/3 times u minus v. And then if I want to eliminate y, let's double the first equation. So 2u plus v. Okay, y is going to be gone. I'll have a 3x left over. So that means x is equal to 1/3 times 2u plus v. All right, save these. We need them for the Jacobian as well as for the integral, yeah? Good stuff. So Jacobian time. Del xy, del uv. Here we go. Partial derivative of x with respect to u, that's going to be 2/3. Then with respect to v, 1/3. Now for y, we'll have a negative 1/3 and a positive 1/3. Looks good. Take that determinant now. You have 2/9 plus a 1/9. We get a 1/3. All righty. Now let's move on, set up our double integral. Always write everything all the way out. So originally you were integrating over r, x plus 2y over cosine x minus y dA. And then since we're just integrating over a rectangle, we just have to decide, we could put v on the outside, u on the outside. I'll do v. So we'll have integral from 0 to 2. Those are the limits on s in the v direction. And then 0 to 1 for u. And then notice x plus 2y, that's equal to v. Over cosine of, well, x minus y is u. And then you've got absolute value of your Jacobian. This is du dv. All right, now notice here, all my limits are constants, and then the integrand is a product of a function of v and a function of u. So I can actually split this up into two integrals for functions of a single variable. So I'll write this as 1/3 integral from 0 to 2 v dv, and then integral from 0 to 1. Now we know we don't want to integrate 1 over cosine u. That's secant u in integration land, du. Okay, so one at a time. That first antiderivative, after we evaluate it, you'd have v squared over 2, evaluated from 0 to 2. It's going to just throw another 2 in the mix, times that 1/3. So that's going to give me 2/3. And then what's the antiderivative of secant u? Do you remember? I hope so. That's why you took Calc 2. It's natural log of the absolute value of secant u plus tangent u. Yep. Evaluated from 0 to 1. Okay, if I substitute in 1, I'll have 2/3 natural log absolute value secant of 1 plus tangent of 1 minus, and then if I substitute in 0, secant of 0 is 1, tangent of 0 is 0, natural log of 1 is 0, so we're done. So that's our answer. Good, very nice. And you could see the antiderivative was pretty easy to compute after we set up the transformation appropriately. Okay, one more fancy little one. This time we get some help with the graphing, okay? So use a change of variables to set up a double integral that could be used to evaluate the double integral over R of y squared dA if R is the region bounded by x times y equals 1, x times y equals 2, x times y squared equals 1, and x times y squared equals 2. And the region R is graphed below. So if it's not clear, allow me to shade it in more for you. So here's the region R, where all the dots are, okay? Let's do a nice dark green. This is R. All right, well, let's transform each of the boundaries. There's 4. I think we already can tell what u and v should be, right? Let's let u equal xy and v be xy squared. So R1, which is xy equals 1, that would become S1, which would be given by u equals 1. R2, which is given by xy equals 2, would become S2, u equals 2. R3, xy squared is 1. So that means S3 would be v equals 1. And then lastly, R4, xy squared equals 2. That becomes S4, v equals 2. Oh, we have the cutest little square in the UV plane now. Just from 1 to 2, 1 to 2. U, V, 1, 2, 1, 2. Okay. And this is S. Let's shade it in. Beautiful. This is my favorite one so far because they gave us the graph, you know? What a help. Okay, I wanted to do this example because it's a little trickier now to solve for x and y in terms of u and v. You have to be a little creative. So remember, u is equal to x times y, and then v is equal to xy squared. So our elimination methods from before aren't going to work. What you can try is, let's take v divided by u, and then xy squared, which is v, I would divide that by xy. That just gives me y. So that means y is equal to v divided by u. Very good. What about x? Well, working with this first equation, I know that x is equal to u divided by y, but now I know what y is, so that's going to be u divided by v divided by u. So x is going to be u squared over v. All right. Now let's go ahead and get the Jacobian. So we have del xy, del uv. Okay, now these partial derivatives are going to be more exciting than just a bunch of constants. I hope you're ready. So partial derivative of x with respect to u, that's just going to become 2u. And then remember, we're treating v as a constant, so just leave it in the denominator. Now partial derivative with respect to v, that's u squared times v to the negative first. So we're going to end up with negative u squared over v squared. Partial derivative of y with respect to u, so think of it as v times u to the negative first, so that'll be negative v over u squared, and then partial derivative of y with respect to v, just 1 over u. All right, so now let's see what's going to happen here. When I evaluate the determinant, I'm going to get 2 over v, right, because the u cancels out right here. And then similarly, the u squared is going to cancel there, so I have 2 over v minus 1 over v, which gives me 1 over v. Now remember, for the actual integral for dA, we need to use the absolute value of the Jacobian, absolute value of 1 over v. Well, how do I deal with this? Well, look at the region. V only varies between 1 and 2. So that means I don't have to worry about it being negative. So since v is always greater than 0, we're okay. Otherwise, you might have to split up your integral. okay, if v changes signs. That means now, remember we were evaluating the double integral over r of y squared dA. So our region's just a cute little square, so we'll go from 1 to 2, 1 to 2. Limits are same for u and v. And I'm integrating y squared. Well, remember, what was y? Y was v over u, so that means I'm going to replace it with v squared over u squared. That's my y squared. And then dA is 1 over v dv du. All right, how would you actually evaluate it? They didn't ask us to, but we of course want to be prepared. Well, again, all my limits are constants, and then the integrand is a product of a function of v and a function of u. So I can break it up into the integral from 1 to 2 v dv times the integral from 1 to 2 of 1 over u squared du. And each of these super straightforward, so you end up with 3/4. All right, so that concludes the lesson. Read up on Jacobi and comment below your favorite fact you learned about him. He's a pretty interesting dude. Don't forget to subscribe and like this video. There's more to come.